So hello everyone, once again, Joel from the OnlineTestConf headquarters here. And we are about to start our next session. Ali, are you here?
Yes, I am.
Okay, great. We can hear you loud and clear. Let me make you the host so that you will be able to start sharing your screen. And I will introduce you in the meantime. So you should be able to share your screen right now. So let me just introduce Ali for a second. So actually, it's cool that you get to meet some people in the testing world, and Ali is one of them. We met briefly in Spain, in Bilbao, earlier this year, where Ali was actually awarded the best presentation or the best session on the Q&A Test webinar or the Q&A Test conference in Bilbao. And he did give a pretty cool presentation over there. So I'm very, very happy that he agreed to join us over here. Ali is from the United Arab Emirates, and he's working actually for Emirates Airline. And he has been in testing for the last 12 years in a number of roles on enterprise system testing, and I'm sure that you will introduce yourself better than I do. So guys, just as a reminder, if you have any questions, the best way to ask them is either via the Slack channel for Ali or via the Q&A. And go ahead, the floor is yours.
All right, thank you, Joel. That was a nice intro. So I'm going to talk about today about big data and how do we test it. So I think Joe pretty much mentioned all I had to, so I don't have much. So I'm working as a test architect, and mainly I spend my time with the quality transformation that is happening. So moving on to our subject for today is big data. Before I start talking about how big data works, I wanted to give you a background of the history, a little bit of history into big data. So centuries ago, we always had data. So data is nothing new. We used to write it on different forms before even we had paper. Then we started printing, we had books, we had lots of books, libraries, and data existed, but in a very different form. Then after the rise of computers, we started with having Excel sheets. And then we added more sophisticated ways, we created simple databases, we came up with very complex, big relational databases. And then something happened, the web took off. And before that happened, everyone used to enter data in person. There was no automatic mechanism of getting this data into our systems. There used to be a person doing it. And the person wasn't just an individual, any person from outside the public. It used to be mostly company employees who would enter data in an ERP system, financials, whatever. So there were a limited number of people who were entering data as well. And the type of data we had was pretty basic, like in terms of it was financial data that we had. It was more about how the system, our payroll, HR system, so on and so forth, but it was pretty structured. And over time, what has happened is, since the last decade, things took a big turn, and social media took off. And with that came a lot of exciting challenges and opportunities. So the first thing, the type of data that we had become very varied. We had audio, video, and data now. It was the public creating data instead of just employees of an organization creating data. Then we also came up with different formats. We had audio, we had pictures, we have videos, and out of all of these, we try to synthesize information and try to process that and make use of it. So the type of information that now we are gathering has also varied. And it didn't stop over there. Now we had smart devices, IoT devices, which also started to pump data. And our systems also became relatively intelligent and complex, where they were creating their own telemetry or data on how the system is being used, different devices, consumer electronics, even creating information. So information creation just didn't stay with humans. A lot of other things also started to create data. And then we also got very good at sharing that data across. Well, so in some cases we might not be happy of that sharing, but the sharing does happen. And in a lot of cases, there's a lot of open source data which exists, for instance, weather data, flight data. A lot of it is still open source, and a lot of people do use and share data across. So all of that, in a nutshell, you have a big variety of data which is being produced not by your employees, but everyone around the world. And you have systems which are also creating that data. And then we also have a mechanism of sharing that data very easily. You can see with all of these variables, we ended up with a large pool set of data. Now, amassing data is no problem. Now, once we have all of that data, processing and saving that data was the challenge. So there were a few key fundamentals which enabled that. First one is commodity hardware, where we say that infrastructure as a service allowed us to get on as much hardware as we needed instead of having an upfront big investment. And your data is all in the cloud, and you pay as you go. So you don't have to get the big servers and host them and maintain them. So you acquire as much as you need, and as when you are no longer you need that infrastructure, you don't pay for it anymore. And storage became very cheap. So I was surprised myself to look at these numbers. So in 1980, of course, it would have been expensive, 0.7 million per GB. That was the price of storing memory. And of course, over the years, it's dropped phenomenally. And in 2003, $1.7 per GB, and 2009, 0.07. By now, of course, you get 100 GB just, as a trial. It's the price of data or memory storage is almost infinitesimal at this point. It's not a cost at all. The final thing was the open source ecosystem. So a very key variable which has caused all of this big data revolution was the Hadoop platform, which was open source. That allowed a lot of companies with almost no barriers to entry. So you can see getting hardware, getting memory usage, compute power was cheap, and the technology to use all of that was open source. So that allowed for a lot of people to come in and contribute. So with all of that processing becoming quicker and easier. And now once you have all of that insight, how does that help? In old days, you used to have the way we shipped software was you burned it on a CD and it would go somewhere and the guys would install it on their system. So even if you have some insights from data, there was no way for us to react. But now, with the web economy, we can react to whatever insights we get from data in real time. Pricing engines, case in point. So the pricing engines, depending on a lot of different variables, compute what the price could be today. So with all of this, eventually, the usage of big data became very, very economical and very powerful. When we talk about big data, usually we talk about size. And in science, a common term, petadata, is most commonly used, and it's a bit hard sometimes to put that in a visual picture. So one petadata, for example, is of course 1,000 terabytes. But then, how much is 1,000 terabytes? So if you have a DVD with your favorite movie, that's 4 GB there. And if you gather 250 movies like that, if you find a big movie rack, perhaps, let's say you stack all of them, and that's one big movie rack with 1 terabyte of data, and that's just 1 terabyte now. Now, if we take this over to 1 petabyte, that is going to be 1,000 movie racks, pretty much a library. And so that is 1 petabyte. Another analogy, Hollywood, since inception in 1916, has created a total of 44,000 movies, as per Wikipedia. Now, 1 petadata can fit in 5 words, Hollywood movies. And Google, until recently, has been processing 20 petabytes per day, which is equivalent to almost 100 Hollywood. So the size, the scale of data has really made a fundamental shift. Now, with all of this, how does it help? Of course, we talked about buying patterns and clickstream analysis. It also helps with sentiment mapping, social media. It also helps with predictive modeling, predictive analysis, for instance, heavily used in financial markets. So there's a lot of use cases for big data, and especially in all consumer-facing industries. Now we move on to what exactly is big data, the definition. So is it just about size? That's usually what people talk about. So the first indicator people say is size. And some people say, all right, if it's more than 100 terabytes, then that's big. But then, if you don't need a lot of compute power, or you can use it in a SQL DB, is that still big? Then you say, okay, no, let's talk about storage. So with storage, if you cannot store more than, if you cannot store that data in a relational database, then that would be classified as big. But then the amount of data is missing. Then you talk about processing. All right, we need parallel processing. Then we could classify as big. So, but we didn't talk about if the data has to be homogeneous or not. It could be of different types, same type. And say, all right, if it uses the Hadoop platform, which is the most common big data platform, then we could consider it big data. Eventually, we reach that, there are 3 variables, volume, velocity, and variety, which are going to be the best measure of to say if something lies or do we need big data technologies for it or not. So let's explore those. So first one, volume. So if the volume is difficult for your organization to work with, 100 TB, you can have any number, but if it's difficult for you to use SQL or relational databases or even non-SQL like MongoDB, even if it's difficult there, then that would be classified as big. Traditional databases cannot be used. Of course, that's an obvious one. Velocity, the speed at which data you are receiving data, and the speed at which you have to respond back the real-time queries that you have to do on your data set. That is going to define it. And then, do you require parallel processing for all of that? And variety is finally, so usually we have structured data, but then you have semi-structured and unstructured. So in structured, of course, we have databases, anything that you can put in a spreadsheet, right? And semi-structured are going to be your JSONs, XMLs. And then unstructured, of course, are video, audio, and all of that. So if you have a variety of data coming through and it's hard for you to process, then it's going to be classified as big. Testing in big data is quite different because usually in web applications, you have the client side and server side. They have very specific functions to do, and that's it. But with big data, it's data coming in, some analytics happening, and analytic results going out. So it's just data in, data out. So you don't even have a UI. It's very different. So it's just all about data going through different filters and stages and being processed. Now let's talk about how big data works. So there is a concept of what we call a data pipeline. So in a data pipeline, you have the first stage is data ingestion, where data coming from different sources. It could be within our own organization. It could be from organization outside, open source data, whatever. So the source of data could be n number. And you get all of that source data and you save it into what you would call a data hub. And from the data hub, you would do some processing and save it into a data warehouse, which is the second stage. And then you would go into the third stage, which is analytics. Now let's talk about all these stages one by one. So the first stage is ingesting data. When we say we capture all the data from different sources and save the data. So sources could be, you could have data coming out of databases directly, a group of databases, it could be APIs, it could be files being dumped on an FTP server. There are a lot of different ways data sharing happens, and there are a lot of different tools which are used to fetch this data, and you might want to do a very minor ETL as well while you fetch them. So let's say depending on whatever sources you have, whatever mechanism you use to pull the data, you have that data, and now it's time to save it somewhere. Now, traditionally, you would have relational, non-relational databases, and that's where we talk about why relational databases are not suitable. So the first thing is they're unstructured. If you have unstructured data, then of course you can't really put it in columns and rows. Okay, so probably you might use MongoDB or non-structured databases, but then the size of data sometimes can be very big, and the process, the speed of writing data, writing files and reading files also hampers. So for instance, if we have one non-relational database, for example, but it's one machine, the only way you can increase compute is by adding more cores and cache and all. But it's still going to have a threshold. No, the problem doesn't stop there. Then you have the problem of parallel processing. Once you've saved this massive data, you need a way to process all of this in parallel, not in series. So that is why the Hadoop ecosystem has this different filing system called the Hadoop filing system. Let's take a very quick view of how Hadoop filing system works. So I hope everyone is familiar with how the common CI tools work, like Jenkins. So if you have a Jenkins instance installed, it would have so essentially Jenkins instructs different slaves what actions to perform. The slaves perform the action, and then they send the results back to master. So essentially master itself isn't doing all the work. It has a lot of different slaves instances which are helping in distributing and getting that work done. Similarly, in Hadoop, there is a master node, which has an entity called a name node, where all the information saved across all the different slave nodes has the location of what data is saved where. And in the slave node, again, you would have a data node as to what data is saved with me and what data is saved across different other slaves. So in this way, the data is spread across different instances. And also a big part of databases is the replication process. So Hadoop filing system by default has a data replication mechanism through which the data is not saved just in one location but in multiple ones. So for instance, if one slave node does go down or is blocked by compute, then you have other slave nodes which you can use because the data also lives on one or two other slave nodes. So in a nutshell, that's how the Hadoop filing system works. So we captured data from different sources, and let's say we saved all of that data on our HDFS. Now what's next? Now once we are in the data hub, the next step is doing the MapReduce process, which is again an ETL mechanism. So we have this unstructured raw data, and we try to extract some meaningful information from this data and save it elsewhere, which we call a data warehouse. And let's have a look at how MapReduce works. So you have this massive input data coming in. We saved all of that data on different slaves. And on each, when we have a query, for instance, I have 100 files saved across 3 different slaves, I have a query that I have to run. So I'll run that query on all the slave nodes separately. They'll run the query, get the results, and then the reduce process happens, where we gather the results from all the slaves, combine them, and you get the output. You see, in this way, the query is running in parallel instead of running in series across that whole data set. Another analogy I really liked was if you want to gather data from a building. So this is a case of Burj Khalifa, tallest building. So if I have to gather data from, let's say, how many people park where, who come to the building, to the office. Do they use the building's own parking, the public parking, use the metro, or they use taxi? So, and we want to upsell products according to how they commute to the office. Let's say that's the use case. So you would have, if you use in the map process, you would have 168 people span across all 168 floors, and at each floor they would float a sheet of papers asking people that where do you park, for example, or do you use public transport. We gather all of those and we combine all those sheets of paper in a folder for each floor, and we pass it through to the lobby to gather all of that data. So that is the map process, where we had a query, we ran that query across our data set and got the results from all the different slave instances and collated all of it. The next step is reduce process. So I have these folders which are sorted by floor now. Now I combine the results into a meaningful form wherein, all right, so these many people travel by this mode, these many people park in such and such area. I do the totals, and eventually I have a master spreadsheet where I have all the results. And this is then the reduce process. So from our diagram again, we had the sheets. We collected all of those sheets from each floor. That is the map process. Those were shipped down, or sent down, and we reduced them into a spreadsheet, and that is the output. So now imagine if instead of having 168 people across all floors, if we had just one person running around the building trying to gather all of that data. That would be a nightmare. So, and that is precisely why for a big data you need parallel processing. So now once we have that information, which is our whatever data we needed from our data set, now it's time to save it. So we had some unstructured raw data, we got some meaningful data. Now this meaningful data it's somewhat structured. We can put it in tables, in columns and rows, but then still not relational databases. So Hadoop also has an answer to that. So the first, we talked about HDFS, and the MapReduce process happens here. Then there is something called HBase. Now with HBase, the data still lives on HDFS, but which data is stored where is in HBase, and it creates columns and rows for that data. The data physically still is in HDFS, but the columns and rows just point to or create a logical representation of that data. So from here on, you have columns specifying that, for instance, in our example, people from floor X parking at the building's parking, people from floor Y parking or taking the metro. So you could save all of that in a wide column database. And then Hadoop also has a lot of there are quite a few querying languages. One of them is HiveQL. So HiveQL essentially for the users is a SQL-like querying language, and we write the query similar to the way we do in SQL Server, but then translates that language into what HDFS can understand. So, and HiveQL could work with HBase or it could work with Hadoop, both of them. So with this, for instance, we say our raw data was in HDFS. Once it was processed, now we can have some structured information in HBase. So let's say our warehouse is in HBase. So we went from our data hub to our data warehouse. The next step is about analytics. Now, just getting that information is of no use unless we do some, unless we use that data for our consumers market. There are a lot of different tools that you can use for analytics, and a big area is business intelligence, BI. And in BI, there are again a lot of different offerings. I'm just taking one example of MicroStrategy here, which is fairly known to me. So in MicroStrategy, from all the data that lives in our data warehouse, we're going to pull it into an Oracle database because it's an Oracle offering. And from here, we create what is called a semantic layer. And in MicroStrategy's language, it's going to be a fact table. So a fact table, essentially, we took data from there. And in our example, we might say 30% people drive or come to the office through metro. X percentage people park in the building's parking. So all of that is somewhat of a model. Now, out of this model, then the platform can do analytics. We can get reports, which is then the front end of this, which is called a dashboard. So the whole idea is you have a lot of data out of which you get some insights, and then you can change the variables and see what different analytics you can get from that data. And again, as I mentioned, there are a lot of different tools and platforms which can be used. I'm giving a very, very high level and very brief picture of what can be done at each stage. So again, we went from ingestion to the data hub and warehouse, and then into analytics. We took some unstructured raw data. We processed it a little in the hub and the warehouse. Then we created analytics, and at the end, we have some dashboards which our customers or the business can consume. In the data hub and warehouse, you can have a lot of different, some places in some companies, they could have the data hub and data warehouse both living in Hadoop. In some cases for data warehouse, they might have a different platform altogether. Similarly for data ingestion and similarly for analytics. And it's quite common, in fact, that a lot of companies do have multiple different warehouses and different analytic platforms as well. So in analytics, you might be using, for business intelligence, you might be using a different tool. For some other, for data science, for instance, you might be using a different tool set. And a lot of cases now, all of this data that we collated and saved, this might be useful for other products or services within our own organization. So we might be just exposing APIs, which is going to expose that data warehouse of ours to other products or services that we have. So the point being, at each stage, you might have a lot of different type of platforms that you might use. Now we go to the topic about right now. Once we have some rough idea of how big data works, we can talk about really testing the process. So in the first stage of data ingestion, we have a lot of data sources. We pull the data and we do some minor ETL in some cases. For instance, let me give an example. We are pulling data of passengers, and there is a timestamp. Now, the timestamp is in a different format than what we want it to be. Now, we've asked the downstream system that, guys, or is an external vendor sending that data, we have no control over how that contract is done, and we're just consuming it. We might want to change the date format a little bit. So that's a minor ETL. So you might use, there are a lot of, again, other offerings. SnapLogic is one of them. So we might do some minor ETL or just pull the data as it is and save it in our data hub, or let's say in our example, HDFS. Then we do the map and reduce process, which you just talked about, which is again one form of ETL. There are many other forms of doing ETL as well. once we do the ETL, it's in the data warehouse. And then in the analytics layer, we have our semantic model, and then we expose the analytics results. So across this data pipeline, the testing is going to happen at a lot of different stages. So the first step is going to be pre-Hadoop validation stage. And at this point, what we're really interested in is any data coming from our sources is correct enough and is complete. Because the challenge with big data projects, if you have a web application and you've developed its functionality, there isn't a lot of information that the users are going to input into the system for anything to go wrong. It's pretty predictive. You know, if you test it well enough, then you know how, most probably how it's going to work in the field. But with big data, the problem is that the big chunk is the data that we are pulling in. And that data can easily, there might be a problem that happens downstream somewhere where we are pulling the data from. And it would just pass through our data pipeline undetected. And it could happen that while we are testing, it works fine, but then a few months down the line, there was an issue or an upgrade that they did downstream somewhere, which is causing this data to probably not render properly, or it's incomplete, or they've changed something, it's coming in a different format. So the first step here is the pre-Hadoop validation stage, where any data coming from source, we're trying to check if the data is correct and complete. So an example of completeness could be, again, if I'm trying to fetch passengers, and I say, all right, now for such and such flight, we were supposed to have so many passengers. If we say, you know, we were supposed to get X, but we are getting Y, there is something wrong. We missed something. Or for each passenger, we were supposed to have 20 fields, we received 10 fields, 5 are missing, there are none, so something is wrong. So that could be an example of complete. Correctness would be that there is some data in there, but is it really correct or not? For instance, if it's a phone number, it has 1 digit less or 1 digit more. If it's and in some cases, yes, we can get some parameters if the value is correct or not, but we can't be 100% sure of the data being correct. For example, email addresses. We can check for the @ symbol in there, but then if an extra letter got added somewhere in the email, we can't be sure if the email is still correct enough. We have no mechanism to do that. So we try our best to have some correctness check and completeness. So once that happens, it's time to save the data on HDFS, and the MapReduce process starts. Now the challenge with MapReduce is, as you've seen before, it can be a very complex ETL, extract, transform, and load process. And what that means, it's no longer an apple to apple comparison. It's apples and you've made, or it's oranges and you've made marmalade out of it. So you can't really compare. It's not a one-to-one comparison. So usually the way MapReduce testing happens, we take a subset of test data and we compute what the expected ETL output should be. And we run it through our MapReduce process that we have implemented and validate the output. Now, of course, the problem there is the test data that we are taking has to be versatile enough to cater for all the different permutations you might get from source. At times, it might seem an easy process, but then it's really hard to figure out all the different permutations that you can get from your source. So that always does come up as a challenge. If on the data warehouse stage, If the data being saved is on a Hadoop filing system, again, from HDFS to HBase, then most probably there is a very slim chance of any data being missed. But if we were using HDFS for saving our data hub, and the data warehouse is a different platform, then it would be, there is a chance that we might lose some data. So if that is the case, then you have to compare the output from MapReduce and validate if it's saved properly in the data warehouse, in the model in data warehouse. This one could be, this one is usually not as complex because the output from MapReduce we know, and when it's saved in the model, usually it's a one-to-one comparison. Now, when we move over to the analytics part, we create a semantic model. So all the data that was in the warehouse comes into the semantic model. That is, again, a bit similar to the level of complexity we had for MapReduce, because probably this may or may not be, again, a one-to-one mapping. So you have to check for completeness, and if the model that the data is being translated to is proper or not. And again, in the semantic layer, the data coming from the data warehouse can be of varied types, and it could be depending on the business use case we have. Models are usually built around, I'm trying to solve this problem, build me a model for it. I'm trying to solve problem X, to create a model for that one. So you might have a lot of different semantic models depending on what business problem you're trying to solve. So once we have our data in the semantic model and we've tested, then we talk about, it's just a matter of all that model data being presented in different formats. It could be dashboards, could be reports, could be perhaps APIs exposed, a number of different forms. And this check again can be a bit easier. So you might have where you just look at what data you have in the model and compare it with what you are seeing on the dashboard, and that can be a bit easier. In cases where you have APIs, for example, you might see that what data lives in my data semantic model or in my warehouse, and is my API that is being exposed, is the data being properly shown through my API. So these are usually the easy ones. So all in all the test stages that we have, you can see that there are a lot of different stages across, and a lot of all of these stages, the types of testing that we do are very varied and very, very different. We did the pre-Hadoop validation, where we check for the data correctness from source. We do the MapReduce process testing, where we check if the ETL has been done correctly or not. Has the data been saved on the data warehouse? Have we done, is the semantic model being built properly? And is the output of the analytics correct or not? As you can see, in some cases, the testing doesn't really have to be, you can have scripts which can do the big laborious work for you, for instance, where you have to check columns or rows of data or file sizes or record counts and compare it with the other side. Of course, all of that has to be through scripts and through an automated fashion. But then, of course, as with all testing, the cases where you have a lot of information, where you're building semantic models out of it, where you're building, saving it in the data warehouse, the MapReduce process, these are all necessarily, you cannot have a completely automated journey. So there are going to be places where you can do automation, and there are going to be places, of course, as with all testing, which you have to really put your heads together and figure out how we have to test this piece. I have to say that the testing in the big data space is in its early stages, as is big data as well. And there is still a lot of, I think, I personally feel that there is a lot of, there's a long way that the testing community has to go in this space. So with that, I think I tried to cover the basics here, and I know it must have been a lot, but you can certainly reach out, and I think we can go through any questions that we have.
Ali, first of all, thank you very much. I think that I actually like the fact that you covered all your bases and you didn't assume that people do know the different stages of big data analysis, and then you covered the testing. So I think it was pretty amazing to have everything in one presentation. So that was pretty cool in itself. There are a couple of questions over here. Wait a second, let's go over that. So one of the questions here, and again, I'm just reading out loud directly from this, based on the evolution of the big data or big data, it hasn't the importance of wait a second, let me read it again by myself. Question here that it's, and I'm going to rephrase it a little bit, given the way that big data testing or big data usage has been increasing in importance lately, has that been also related to security testing? Do you see any correlation or even, let's say, collaboration between big data testing and security testing on that? And a second, well, you know what, I'll take the second question later.
Okay, all right. So yeah, security, and not just security, GDPR also is a very massive problem. And of course, the race between is your data securely saved, how much can I expose to the rest of the world, how much I have to keep hidden. Then GDPR raises a very, very problematic case as well, because then, you know, what kind of data I can save for a long time, what data I cannot save, what data has to be shared with whom, the right to be forgotten, and all of that. There are a lot of cases where, you know, it does become very tricky. And in my experience, it's still, I think it's evolving in terms of security and GDPR as well.
Okay, another question here, and this was something that actually jumped to my mind as well. Can the testing of the pipeline be conducted in parallel? Basically, what I was imagining is, can you have some sort of end-to-end smoke testing that will help you just to give like a quickly one go before you start going very deep into the different stages? And if it does, would it save time at all?
Yes, that's a good question. So because of time constraints, you have no idea how many slides I removed from this. And I try to cover some of that there. So in a lot of cases, it depends on how mature your data pipeline is, or even if you have a data pipeline. In some cases, they don't even call it a data pipeline. It's just like we have dumped some data and we're just trying to do some analytics on it and just push it out. So it really depends on the maturity of your pipeline. In a lot of cases, especially in big data, there are two types. You have stream jobs and you have batch jobs. In stream jobs, everything is, of course, real time. As soon as you get something, it gets processed. In batch jobs, it's after a certain interval, mostly 24 hours, after 24 hours or something. So it depends on what kind, you know, how your pipeline is set up. But I have to say, with regards to that question, there are two things which have to happen. Of course, you need to have a data set which you push through source and you verify it at the end at your analytics as a smoke test. regardless of if it takes less time or more time, that is something that absolutely just has to happen. Because in a lot of cases, we just feel like if it's the same thing as if unit tests are working, then do we really have to do system integration tests or integration tests? It doesn't necessarily mean if unit tests are working, then the whole system works. You have to check the whole system. The second thing is, the problem with data, with big data, is a lot of this depends on what kind of data you're sourcing, you're getting from source. So just testing before production doesn't solve the problem. You have to test during production. And you have to be careful. You can't put a lot of load on the system just because you're testing, but some tests have to happen. You sample a few bits of it so that if something fishy starts to happen in the source, you get to know. Otherwise, you have no indication, and it would just somehow in some creepy shape or form start reflecting in your analytics, which puts the whole data pipeline's authenticity in jeopardy.
Got it. So I think it's a good place also to understand that, yes, even in big data or especially in big data, we will need also to look into testing in production as basically a way of working, because there's no other way around it. You will simply need to do it. That's actually pretty cool input. I hadn't thought about that as well. So Ali, thank you very much for the time here. There is another question. I hope that you can take it actually. A couple actually. People, please go ahead and write them on the Slack channel. Ali, I hope that I'm not putting you too much into that. He will try to answer them on the Slack channel there, guys. Thank you very much for your time. It was a great session. Thank you.